Hello guys, welcome once more to another new video again in my channel. So in today's video we will be looking at the advanced level mathematics with mechanics. Okay, so in this mechanics we will be looking a topic called motion of connected particles and Newton's laws of motion. Okay guys, so this video is actually dedicated to advanced level students doing mathematics with mechanics. That is for the S1 S2 students. Okay, so please, as I always recommend to my videos, subscribe to the channel so that you will get more of these videos. Share to your friends so that they can also benefit from it, and stay tuned for more uploads. Okay, so please, diving into this topic will be your great way for you to mastermind the motion of connected particles and Newton's laws of motion. Okay, so before we begin, please look for your book and a pen and possibly a scientific calculator so that you will follow me step by step, get the relevant points. In fact, in this video, I'm just going to give the direct procedures to handle some cases when it comes to connected particles and Newton's laws of motion. Okay, because we'll be using the Newton's laws to solve this all these stuffs on the connected particles. Okay, so let's get started. All right, so we'll begin with Newton's laws of motion. Okay, so we'll be looking at the laws of motion. Okay, so Newton's first law states that a body at rest will remain at rest, or when in motion travels with uniform velocity in a straight line unless acted upon by an external force. Okay, so I hope it is clear. The law is clear. A body at rest will remain at rest. It means when something is at rest, it will remain there forever. But when it is in motion, it means it will also travel forever along a straight line unless it is acted upon by an external force, which means that the body can only come to rest if an external force is actually acting on it. So actually there are no demonstrations of this law, but I decided to come out with mine as we are going to see. So if I consider a body lying on this surface, right? So let me say this body is at rest. Okay, so this one is at rest. Okay, and I will set this in motion after explaining this. Okay, let me say this body is at rest. It is at rest. Okay, so it means that this body, since it is at rest, it will remain here forever at rest. Okay, but when an external force acts on it, it will continue to be in motion. Okay, like let me say if I set this ball in motion now. Okay, so if I set it in motion, it will continue to move in this direction. Okay, so if the ball is in motion, it means it will move with constant velocity in a straight line forever. Okay, provided there is no force acting on it. But if I decide to roll this ball and then it comes to rest, it means there is an external force acting on it, and that force can only be friction since the ball is actually coming to rest. Okay, so that is a better demonstration of this Newton's first law of motion. That is, this will remain here at rest forever if there is no force acting on it, and this will always continue to be in motion forever, but will stop if an external force is acting on it. That force can be friction, or it can be a drag force, and or any other. Okay, so let's look at the second law. Newton's second law. Newton's second law states that Newton's second law states that the rate of change of linear momentum with respect to time is directly proportional to the resultant force and acts in the direction of the force. Okay, so this is the force here. Okay, so we have F equals force is directly proportional to the acceleration. Okay, so it means that if force increase, the acceleration increase, and if the force decrease, the acceleration also decrease. Okay, so it means force and acceleration are directly related. Okay, so what does that mean? So we have, if we bring in a constant m, so we have F being equal to mass times acceleration. So this is the mass of the body, and this is the acceleration of the body. Okay, so this is not actually the acceleration due to gravity, this is the acceleration of the body. Okay, so that is it. So we can consider this law So we can consider this law as a bullet being fired in a gun. Okay, so the bullet will only move in the direction of the force. Okay, I hope it is clear. Like, since the force is acting, let me say the force is acting to the left, right, it means the bullet will actually move to the left. Okay, so that is why the rate of change of linear momentum, so momentum will always change in the direction of the force. Okay, that is why a player can actually direct a ball which was kicked by a player, or let me say a player crossing a corner kick. So if the other player can only direct the ball to the pool, it means the player changes the momentum of the ball. Okay, so that is what the second law is actually saying. All right, so let's look at the third law. The third law states that when a body A exerts a force on the body B, then body B exerts an equal but opposite force on A. Okay, so that is FA is just equal to negative FB. Okay, all right, so in this law, I decided to demonstrate an important demonstration. Okay, so if we consider our surface and we consider a car, we consider a car hitting a wall. Okay, so this is our car hitting this wall. Okay, so it means that if this car hits the wall, this wall with a velocity that we don't know, we are not actually interested in the velocity, it means that the car exerts a force on the wall, and equally the wall also exerts a force on the car, but just that the force that the car exerts on the wall is equal to the force that the wall exerts on the car, but is that the force that the wall exerts on the car will be opposite. Okay, will be opposite to the force that the car exerts on the wall. Okay, so if you consider this red arrow, red arrow as the force that the car exerts on the wall, and we can call that force FWC. This FWC means that if you call W the force on the wall and C that of the car, right, it means that this is the force on the wall due to the car. Okay, so this is the force on the wall due to the car, and equally the wall will also exert a force on the car, and we can call that force FCW. It means that this is the force on the car due to the wall. Okay, so it means that even you can actually let me say you want to hit a wall, right, with your hands. Okay, so if you hit the wall, you actually notice that you actually feel your hand. Okay, because you exert a force on the wall, and that force that you exert is just equal to the force that the wall also exerts to you. Okay, so that is a better demonstration of the Newton's third law. All right, so let's continue. All right, so let's move now to motion of connected particles. Okay, so in this motion of connected particles, we will just be looking at the various cases, because I did this not to make the video to be too lengthy. Okay, so that is the reason of me doing this. All right, so let's look at it. So the case one, okay, we'll begin with the pulley system. Okay, so let's look at the pulley system. So this is our pulley. This is our pulley with mass A and B hanging freely. Okay, so um this is our two masses, right, A and B. Okay, and we actually have our tension here. Okay, so this is our pulley, and there will be a normal reaction. There will be a normal reaction on this pulley. Okay, so if we call this force the normal reaction, why? Because actually this mass B, right, this mass B and mass A, right, will actually be exerting the force that this mass B is exerting, and this mass A, the force is actually called the normal reaction force on the pivot. Okay, so that is our normal reaction force. Okay, but on this string, right, we have our tension. This is our tension here, and we have another tension here. Okay, so these are actually our tensions. Okay, so this tension, you notice that they are actually equal. Okay, the tension are equal. That is why they are not labeled T1 and T2. Okay, so we can actually, this is the weight that mass A exert. So the weight that mass A exert is called MAG, and the weight that mass B exert is also called MBG. Okay, so that is it. All right, so from here, right, we can actually apply Newton's laws of motion. Okay, so let's look at how we can actually tackle that. All right, so that is an important thing that I want you all to know about. So you notice that the mass of particle A, right, is actually less than the mass of particle B. So if the mass of particle A is less than the mass of particle B, it implies that the mass of particle B is greater than that of mass of particle A. And if that happens, it means that this system is just going to accelerate in this direction, okay, in the downward direction. And if that happens, we can actually label the acceleration. We can actually show that the acceleration of the system is actually going downward, okay. So that is it. All right. Um, let's look at things. So from here, right, if we apply the Newton's laws of motion from the diagram, right, applying Newton's laws of motion, we will have that our mass, we will have that our mass B, the mass of the weight of B, sorry, the weight of particle B minus the tension will be equal to the mass of particle B, the weight of the mass of particle B times the acceleration. Okay, so if we come here, right, if we come here, why do we decide to take the weight of particle B minus the tension equal to the mass of particle B times the acceleration? Okay, so this is due to the Newton's second law. Okay, so by Newton's second law, we notice that force is equals to mass times acceleration. So what is our force? So we have two forces here actually acting on this body. So if we apply Newton's law, this law here, it means that we will look for the resultant force, and the resultant force is gotten by taking the bigger force minus the smaller force and equate it to the mass of the system or the mass of the body times the acceleration. Okay, so that is why we have this. That is why we have this here. Okay, how does it work? You notice that since this system is actually accelerating in this direction, it means that the weight of particle B is greater than the tension. Because if the tension was greater than the weight, it means that this particle B was supposed to be accelerating upward. But since the weight is more than the tension, that is why it is accelerating downward. And therefore, the weight of particle B is bigger than the tension. That is why I have to take the bigger force minus the smaller force, or the bigger force minus the opposing force. Okay, that is why we have mass of weight of particle B minus the tension equals to the mass of particle B times the acceleration. And we can conveniently call this equation 1. Okay, so let's move now to the motion of particle A. Okay, so for the motion of particle A, how is it going to be? So we are going to look for particle A. How is it accelerating? We notice that mass of particle B is greater than mass of particle A, and therefore it means that particle B will be pulling particle A. Okay, so if particle B is actually pulling particle A, it means that particle A will be accelerating upward. And if particle A is accelerating upward, it means that the tension force is bigger than the weight of particle A. And if that happens, it means that we are going to take T minus weight of particle A equals to the mass of particle A times the acceleration. Okay, so at the end of the day, we'll have the tension minus the weight of particle A, which will be equal to the mass of particle A times the acceleration. And we can conveniently call this equation 2. Okay, so that is it. All right, so from here now, you can actually solve equation 1 and equation 2 simultaneously. So how is it going to be? Notice something that we have, if we solve these two equations simultaneously, right, we notice that here is negative t and here is positive t. So if we take a negative number plus a positive number, the answer will be 0. Okay, so if you add equation 1 plus equation 2, this t will actually fall out. Okay, and if t fall out, we'll be left with the weight of particle B plus minus the weight of particle A, which will be equal to the mass of particle B times acceleration plus the mass of particle A times acceleration. So at the end of the day, we'll have this. Okay, so we'll have the mass of the weight of particle B minus the weight of particle A, which will be equal to the mass of particle B times the acceleration plus the mass of particle A times the acceleration. Okay, so from here, right, we can actually factor out acceleration. So what they will always give you here is that they will always give you a system that calculates the acceleration. From the acceleration, you can calculate the tension, and from the tension, you can equally calculate the reaction force. Okay, so from here, you can actually factorize. We can actually factor out A, since A is common. Okay, so if you factor out A, we'll have that the weight of particle B minus the weight of particle A will be equals to the mass of particle B plus the mass of particle A times the acceleration of the system. So this is the acceleration of the system that we are about to look for. Okay, so that is it. So if we work out things clearly, if we divide all through by this term here, we'll have that as well as our acceleration will just be equals to the weight of particle B minus the weight of particle A divided by the mass of particle B plus the mass of particle A. Okay, so that is it for the acceleration. So please, this procedure is very important, or these procedures are very important because we will be seeing them. Okay, so that is it. All right, let's continue. So this is our acceleration. So you follow this procedure for pulley systems for you to find acceleration. Okay, so now to calculate the tension T, substitute A in either equation 1 or equation 2, and the reaction R is just equal to 2T. It means since this particle is actually exerting a force on this pulley, and that force is actually the tension force, and also particle is also actually applying a force on this pulley, and that force is actually the tension. That is why we have to take the force of the two particles, which will be 2T. Okay, so that is it. All right, so let's look at an example on this. Okay, so two particles of masses 8 kg and 7 kg are connected by a light inextensible string passing over a fixed smooth pulley. Calculate A, the acceleration of the system; B, the tension in both strings; C, the reaction in the pivot. Okay, and take G as 10 meter per second squared. Okay, all right, as I earlier told you, you notice that most questions they will always ask for the acceleration first, so that you use acceleration to calculate the tension, and if equally ask the reaction, we also use that tension now to calculate the reaction. Okay, so that is it. All right, so let's look at the solution now. Describing from the problem, right, you can actually draw the diagram, because in math mechanics what they recommend, or what is actually required is a diagram too. Yeah, they actually, because from a diagram they know what you are actually doing. Okay, so if you draw a diagram now, so you will notice that we have our 8 kg mass and our 7 kg mass. Okay, so 8 kg mass we have weight 8g. This G is not actually just gram. It's not. It doesn't mean 8 gram. It means 8 times the acceleration due to gravity, which is 10 meter per second squared. Okay. So equally, our 7 kg mass will have weight 7 G. Okay. So this weight means you take the mass times the acceleration due to gravity, which is 10 meter per second squared. So that will actually equally give your weight. So it depends on you. Okay. All right. So from here, right, we can actually apply the Newton's law. This law here, we can equally apply this law. So if we apply this law, what are we going to have? You notice that here, right, since 8 kg mass is more than 7 kg mass, it means that you actually know where the system is actually accelerating to. Since 8 is greater than 7, it means that this system actually accelerates downward like this. So it means if you apply Newton's laws here for this 8 kg mass, we'll have that since it is accelerating in this direction, it means this 8 kg, this force is greater than the tension. That is why this force is going downward. So since this force is greater, it means that we'll take this force minus this other force, which will be equals to the mass of this particle times the acceleration of the system. Okay, so if we do that, we are going to have this. Okay, and we can call that equation 1. Okay, similarly, since this other particle is moving upward, not downward, because this 8 kg is greater than 7 kg, it means that this 7 kg will be accelerating upward. And if that happens, it means that the tension is greater than the weight. Okay, so if that happens, it means we'll take our T minus 7g, which will be equal to 7 times acceleration of the system. Okay, so we'll have this. I can conveniently call that equation 2. Okay, so from here, applying the same procedures, we can actually solve 1 and 2. Since here is negative T and here is positive T, you can add 1 and 2. Okay, so we'll add the two equations. Equation 1 plus equation 2, we'll have this negative T plus T is 0. So we'll have with the weight of the 8 kg mass, the weight of that 8 kg mass, right, plus minus the weight of that 7 kg mass. Okay, it will give us 15A because 8 plus 8a plus 7a is 15a. Why do we add this? Because from this procedure, right, if we add equation 1 plus equation 2, this will be added to this and we'll have this. Okay, that is why here we also have this. Okay, all right, so from here we notice that 8g minus 7g is g. Okay, so our g is just equal to 15a. Okay, but we are actually looking for a, not g. Therefore our a will be g over 15, but we know that our g is 10 meters per second squared. Therefore our acceleration is 10 divided by 15, which is 0.67 meter per second squared. Okay, so that is it. All right, so let's move to the B part, the tension in both strings. So it means that they're actually asking for the tension in both strings, the tension here and the tension here. But since we know that this tension here is just equal to the tension here, it means we can actually calculate just one of the tension, then we conclude for both tensions. Okay, so let's look at it. All right, so that is it. So that is our B part. So from equation 1, right, from equation 1 we know this is our equation 1, 8g minus 70 equals to 8a, and then we already know acceleration. Okay, so if we substitute this g with that, we know it is 10 meter per second squared, and then also substitute this a, that we know it is 0.67 67. It means that from here I can actually calculate our t. So this times is 80 minus t equals to 8a. So if you substitute our a here, it means we have 80 minus 8 times all of this. Okay, so at the end of the day our t will just give us 74.64 newtons. Okay, so that is it. So for the C part, right, from the diagram, since the tension are the same, therefore T equal to 74.64 newton. Okay, so that is the tensions in both strings. Okay, all right. So for the C part, now we should calculate the reaction in the pulley, as we see for the first cases where we were deriving where we were actually looking for the acceleration and the tension. We notice that for pulley system, just take the tension times for that particular pulley system. Okay, where you just have two masses, so we just take our reaction force as 2t. So it means we are going to multiply this t value by 2 for us to have our the reaction force as 149.28 newtons. Okay, so that is it. All right, so let's look at the case 2. So for the case 2, we have particles connected on a smooth table. Okay, so it means here we have a particle connected on a table with another particle hanging freely. Okay, so if I consider this is my table, right, and this is my pulley, so this is my table, so this is my pulley here, right, then I place a particle A and another particle B hanging. Okay, so we have this, so this is my particle A and this particle B is actually hanging freely. Okay, all right, so if I decide to put these tensions to be the same, actually the tension actually the same. Okay, tension here is just equal to the tension here. Okay, and then this particle A we have weight MAG and particle B equally. Actually there will be a normal reaction force here. Yeah, there will be a normal reaction force here that we can label it as N, normal reaction force. Okay, and particle okay, this is our reaction force. Okay, so this pulley, this reaction force on this pulley, right, so we can call it rho. Okay, and equally our particle B we have with mgb. Okay, all right, so from here now, right, from here, okay, we can see that this particle is hanging. Okay, so it means that if this particle B is more than the mass of, if this mass of particle B is more than the mass of particle A, it means that this system actually accelerates in this direction. And if that happens, we can equally apply Newton's law again. So that law is very important. So if we apply that law, we'll look for acceleration and the rest. Okay, all right, so motion of particle A and B. Okay, so from Newton's law for particle A, right, you notice that there is no other force in this direction since the table is actually smooth. So if this table is rough, it means there will be a force in this other direction. But since the table is smooth, it means there is no other force acting in this direction. So we just have the tension. And we cannot take this normal reaction and this weight force, because this normal reaction we cancel with this weight force to balance this particle A to be at rest. Okay, so these two forces actually cancel out. So we are left only with the tension. Therefore, we have T equal to mass times acceleration. So notice that this other one here is just like the Newton's law directly, the Newton's second law. Okay, so that is it. All right, let's move to particle B. Since there are two forces, right, we have this force downward and this other force upward. But since the system is accelerating in this direction, it means the resultant force is this the weight of particle B minus the tension. Okay, that will give us the resultant force. Okay, so at the end of the day, we'll have the weight of particle B minus the tension equals to the mass of particle B times the acceleration of the system. So this acceleration A here is actually the acceleration of the whole system. Yeah, that is it. All right, so now again, you notice that our equation 2, right, we can actually, for us to solve these two equations simultaneously, we can actually you notice that here is negative, here is positive, so we can add the two equations. Notice something here, there is no something anything minus t here or t minus something here, since there was only one force. Okay, so it means that we can consider 0. So let's just say consider something like a 0 plus t or t minus 0. Okay, so let me first of all work with the case. So if I add this plus minus this, it will give me 0, and then 0 plus something this, let me say something plus this, or let me say 0 plus this will give me this same thing here. That 0 that I'm putting there is for convenience, so that you know that there is another term here which we actually add to this other term, because some students might be confused why we just have a t here. Actually, I've explained that earlier. Okay, so if we solve 1 and 2, at the end of the day we'll have mbg equal to the mass of A times the acceleration plus the mass of B times the acceleration. Okay, so for me, acceleration is common. We can actually factor out the acceleration. Okay, so at the end of the day, we'll have this part equals to mbg. Okay, it means I've just reversed the equation. So I have ma plus mb times acceleration. There's nothing different here. If I decide to multiply this acceleration through, I will still come back here. Like me saying A times mb, I'll have mba. A times ma, I will have maa. Okay, so it's the same thing. So for me, I can actually look for the acceleration by dividing through by this ma plus mb. So if I divide here by ma plus mb, I divide by ma plus mb. This ma plus mb the denominator, we cancel this other ma plus mb in the numerator. Okay, so at the end of the day, my acceleration will just give me mb divided by ma plus mb. Okay, so that is my acceleration. All right, so to get a tension, so for us to have this tension, since the tensions are actually the same, maybe you can just calculate what one of them and conclude for the other. If the equation is talking of the tension in both strings. Okay, so to get a tension, substitute A in either equation 1 or equation 2. So it's the same procedure. It's the same procedure. So if we decide to do that, we'll have that our if we substitute that tension, right, this A, right, we'll have our tension, and equally our normal reaction R will be 2t cos theta on 2. Why is it 2t cos theta on 2? Actually, we have a tension. This particle will exert a force on this pulley, which is T. That force is tension. And this other particle we exert another force on the pulley, which is still the tension. That is why we have two of the T's. And then cos theta on 2. Why? Because if you come here, right, this is a right angle, this is a right angle, which is 90 degrees. And you notice that the reaction force actually divides this 90 degrees into two equal halves. That is why we have cos theta on 2. So you can actually conclude problems of this nature, right? You can just say that it is 2t cos 45 is the same thing. Okay, so cos theta on 2. So it depends on you what will be theta. We already know that theta is actually 90. Or here it's actually 90. Okay, so that is it. All right, so here when the table is rough, so as I was saying, when this table is rough, right, it means when this particle will be accelerating in this downward direction, the friction force will be acting on particle A, and that will create another force in this direction. Okay, so that is it. All right, so here we have now that T minus mu n, because here is just T. So now that there will be two forces, these are opposing force. It means we take the resultant minus the opposing force to give us the mass times acceleration. So this mu n is just equal to friction. Okay, so friction is equals to nu. So this nu is the coefficient of friction, while this n is the normal reaction force. And this normal reaction force, for you to get n right, just equate n to be equal to mag, or just equate any normal reaction force to be equal to the weight of that particle. Okay, all right. So I hope it is clear. So here we are not going to solve any example because the video will be too lengthy. Because it is clear that the procedures are the same, so you can just apply to get the order to solve any of this problem of this form. Okay, all right. So for the case 3, we have now 3 particles connected on a smooth table. So now we have 3 of them. So please take note. All right, so three of them now. So it means here we have another particle connected in this other direction. All right. So if I draw my table, right, this is my table, and I'll put the various particles there. Okay. So that's my particle B. These are my pulley systems. Okay, yeah, pulley 1 and pulley 2. So this particle B will connected to particle A, and the particle A we have weight MAG, and we have to attention here T1, T2. Okay. So for the particle B, right? For a particle B, we have particle C. Sorry, particle C equally have weight mcg. So this is the weight of particle C. And then this you always notice that this tension are always the same, but this tension here cannot be the same with this other tension here. Okay, because the mass here will actually be different, and the mass here will actually be different. Okay, yeah. So that is why this tension here and this other tension here are totally different. All right. So our particle B also we have weight mbg, and there will be a normal reaction force n. Okay. All right, so everything now here is done. So let's now move to our reaction, a normal reaction. You notice that for this particular case, right? So it means here we just have one normal reaction, which is just arrow, but here we have two, since we have a pulley here and another pulley here. Okay, so we have the first normal reaction, we can call it arrow 1, and the second one we can call it arrow 2. Okay, it means that since from here, right, since from here r equals to 2t equals theta on 2, or 2t equals 45, right, it means that our r1 will also be 2t equals theta on 2, and our r2 will also be 2t equals theta on 2. Okay, so it's the same thing. All right, so from here we can actually apply our laws, the Newton's laws. Okay, so if we consider the fact that mc is greater than mb, so this is our mc. If this mc, this our mass c is greater than mass b, it means that the whole of this system accelerates in this direction. Okay, you can still consider that it's greater than mass A. It means if mc, the mass of C, is greater than particle B and particle A, it means that the system accelerates in this direction. Okay, so if we apply our laws now, if I apply the Newton's law, right, so for particle A, what are we going to have? Since the system is accelerating downward like this, it means that this force is less than this other force. So it means T1 is greater than this weight of particle A. Okay, so at the end of the day, that's why we have T1 minus weight of particle A equal to the mass of particle A times the acceleration. And we can call that equation 1. Okay, so for particle B, let's look at particle B now. So you notice that the system is accelerating in this direction. Okay, since the system is accelerating in this direction, it means that the resultant force pulling this particle B in this direction is a tension force, the T2. So that is why we have the bigger force T2 minus the smaller force T1, because particle B is actually moving like this. That is why we take this minus this for us to have MBA. Okay, so we can call equation 2. And equally for particle C, since this force is going downward, but this force is actually going downward too, but it is opposing this force. This force is opposing this force, so we take the resultant force minus that other force, or the bigger force minus that other force, for us to have the weight of particle C minus T2 equals to that. So this is our equation 3. So we can see that clearly that from equation 2, right, we can make T2 the subject. So if we make T2 the subject from here, we can substitute it now in equation 3. Okay, so if you make T2 the subject from equation 2, we have T2 equals to MBA plus T1. Okay, so then we can substitute it now in 3. So we substitute this part here in this equation 3. It means we'll have the weight of particle C minus we open our bracket, then we'll put all this term here, then we'll close the bracket, equal to all this. Okay, so let's look at it. All right, so this is our equation. So this is the part that we make T to the subject. Okay, so and this is our equation 3. So if we substitute this in this equation 3, it means where we see T2, we put all of this inside. Okay, so at the end of the day, we have the weight of particle C minus all of this equals to the mass of particle C times A. Okay, so at the end of the day, we'll have weight of particle C minus weight of particle B minus T1 equal to the mass of particle C times the acceleration. So we can call this equation 4. And we can conveniently see that we can solve equation 1 and equation 4. Okay, so our equation 1 plus equation 4, right? So this is our equation 1 and this is our equation 4. So notice that while equation 1 we have the T1, equation 2, equation 4 we have a T1 also. So this is a positive T1 plus minus T1. So that will give us 0. Okay, if that gives us 0, right, it means we'll be left with negative MAG, then plus positive MCG, plus, in fact, negative MAG plus bracket of all this. It means you put all this in bracket plus all this in bracket, right? All this weight of MC. Don't forget that this has cancelled out there because it is 0. So we'll be left with this, this, and this. So if we take negative of this plus plus all of this, if we expand the bracket, right, it means that we'll have, if we expand the bracket and then rearrange. So we'll have MCG minus MAG, then minus this other MBA. So I've just rearranged it. Okay, so at the end of the day, I'll have MCG minus MAG, or the weight of particle C minus the weight of particle A, minus the mass of particle B times the acceleration, equal to mass of particle A times the acceleration plus mass of particle C times the acceleration. Since I have acceleration, means I will send this other one this other side. Okay, so at the end of the day, I'll have MCG minus MAG equals to all of this. Okay, then I can factor out acceleration because it is actually common. So at the end of the day, I'll have this. Okay, then I can divide all through now by this term that is disturbing this acceleration. So at the end of the day, my acceleration is MCG minus MAG divided by MA plus MC plus MB. Okay, and then from the diagram now, as I earlier told you, R1 will be 2t equals theta on 2, and R2 will be 2t equals theta on 2. Okay, so that is it. Then for the rough table, right? For the rough table, we'll have, for the rough table now, for the rough table, notice that it's only the particle B that is on the table, no any other particle. So it means that for the roughness will actually affect just particle B because it is a particle B that is on the table. Okay, so it means for the rough table, since we had T2 minus T1, right? So it means for the T1 there will be two forces. It means that T1 will be opposing T2, and the friction also will be opposing T2. That is why we have T1 plus mu n, okay, equals to the mass of particle B times the acceleration. So where n is the normal reaction which balances the weight, as I earlier said. So for you to look for n, just take the weight that balances n. Okay, all right, so that is it. Hence T2 equals T2 minus T1 plus mu mbg. So this is the weight that has we have replaced with this n. We have replaced n with this weight. Okay, because you cannot just know n like that. For you to know n, we balance, we look for the force that matches with this normal reaction. Balance it. This point here means balances the weight because the particle is at rest normally. So it means the normal reaction will cancel with the weight. That is why the particles sit freely on the table. All right, so that is it. All right, so let's move to the next case. Sorry that I did not indicate the next case. So this is a case where the particle will be placed on an inclined plane. Okay, so if I draw my inclined plane, right, then I label it at an angle theta, then I place my particle A there. So this is my particle A, right? Then I will have this particle A will have weight MAG, okay, and we have normal reaction N, okay, and equally, okay, this is my weight, right? So if I resolve the weight, right, I will have the perpendicular component and the parallel component. So I have the component of the weight perpendicular to the plane and the component of the weight parallel to the plane. Okay, so the component of the weight parallel to the plane is MGA sine theta. Why? Because here was supposed to be white so that I can actually notice what I'm saying. So you notice that this angle is just equal to this other angle here. Okay, yeah, this angle here is equal to this angle here. Like when I was supposed to draw this place complete. So notice that this will be a right angle, the right angle triangle also. So such that this will be my sine and this will be my cos. Okay, that is why we have mg sine theta here, and equally we have mg cos theta in this other direction here. Since this is our component of the weight perpendicular to the plane and component of the weight parallel to the plane. Okay, all right. So this is my pulley system, right? And then I will place my particle A on it, my new particle. Okay, so this is my particle B. Okay, this is my particle B, and then these are my tension, and you know that the tension must be always the same. They are actually the same tension. Tension is just equal to the same tension here. Okay, all right. So this is my angle that my normal reaction force is going to be placed. Okay, all right. So my particle B will have weight MBG, and that is it. All right, so if I place my normal reaction force, right, so my normal reaction force, I can call it R. All right, my reaction force, sorry, not normal reaction, this is the reaction force. Okay, all right, so if that is done, what do you notice about the reaction force? You notice that if I was to complete this pulley, right, this will give me, there will be a right angle here which will be 90 degrees. Okay, and we know that the interior angles of a right angle, or the interior angle in a right angle triangle, right, will sum up to 80. So it means that I'll have 90 plus theta plus this, which will give me 80. Okay, all right, so it means that if I take 90 minus theta, I will have this angle. Okay. If I take 90 minus theta, I will have this angle. If I take 90 minus this angle, I will have theta. So now I will take 90 minus theta for me to have this angle, so that I can solve for my reaction. Okay. All right. So this is my component of the weight perpendicular to the plane. Okay. All right. So motion of both A and B. Okay. So if I consider the motion for particle A, right? So you can notice that if the mass of B, if the weight of B, or if the mass of B is greater than the mass of A, right, it means this system will be accelerating downward in this direction. Okay, so in the equation, it will depend on the equation. Okay, so actually depend on the equation. They might still tell you that this particle is sliding on the inclined plane like this. Okay, so you notice that now it means that the mass of particle A is greater than that of particle B. So now if you consider the fact that the mass of particle B is greater than that of A, means this system accelerates in this direction. And if that happens, it means the motion of particle A, since the system is going in this direction, it means the tension is bigger than this other force here. Okay, so if that happens, it means we are going to take T minus mg sine theta equal to the mass of particle A times the acceleration, and we can conveniently call that equation 1. Okay, all right, so again, for particle B is the same thing. Since this particle is accelerating downward, it means that this force is actually bigger than this other force here. Okay, that is why we have mbg minus t equals to mb times acceleration. You can call that equation 2. And if you add equation 1 plus equation 2, this tension actually disappear, and we'll be left with negative mag sine theta. But for you to take this plus this, it will be somehow odd. So you just go for it to put a positive term first, then minus the negative term. But it doesn't mean I subtracted the equation. No, I add the two equations. But just that if you add it, it means here will be negative, which will be funny. Like it will be negative of this plus this. So it's better for you to just reverse it so that you get plus positive of this, then minus this. Okay, so we have this. Okay, so if I add this MAA plus MBA, I will have MAA plus MBA. Now I can just factor out the acceleration, so that I will be left with all this. Okay, so now for me to look at my acceleration, I will just divide all through by MA plus MB, and if that happens, at the end of the day, I'm going to have my acceleration as this. Okay, and equally, in order for you to have the tension, right, just substitute this acceleration in any of the equation, either equation 1, either in equation 1 or in equation 2. You will still have the tension. So it's the same thing. All right. So what are we going to do now? Next is for us to talk about the reaction. So for the reaction arrow, we have 2t cos 90 minus theta on 2. Why? Because this reaction, right, this reaction force, okay, divide this angle into 2 again. Okay, since it divides this angle into 2, but we know that 90 minus theta will give us this angle. So 90 minus theta will actually give us this angle, but the reaction divides that angle into 2. That is why we divide by 2 here. Okay, so that is it. Okay guys, for the next cases, I think I'm going to upload that in another video for us to actually reduce the lengthiness of this video, because that might actually increase the cost of your megabyte. Okay, all right, please stay tuned. So this video, please, I recommend that you share this video to your friends. It is very, very important. So in our WhatsApp forum, PDF notes are being shared there, well explained, and for the understanding of students. All right, stay tuned for more videos by subscribing to the channel. Okay, so this is very important for you to achieve most of these videos. You have to subscribe to the channel, because if not, if that is not done, it means you will not see some of the videos that I'll be uploading. Okay, you can only go to the channel and search for my channel before you can see the videos. But if you subscribe to the channel, you actually see most of the videos. Okay, Please don't forget to share the channel to your friends so that they can also benefit, especially those of you that are actually writing, because this topic might be treated to you, but it has been long ago. So this video can actually help you for revisions. Okay. Alright, stay tuned for more videos on math mechanics and other videos, physics like data analysis, plotting graphs, most students complaining for skills and the rest. Okay, and even ordinary level, share the channel to your ordinary level students. The channel link you can ask me in our WhatsApp forum, and then you will access it there. Alright, so if you are interested in the WhatsApp forum, you can contact that telephone number there, so that I can be added in the general WhatsApp forum where we share ideas there. Alright, thank you all for watching. See you in the next video.